It's just like, watching TV at the same time.
Does anyone sit here?
Yes. Xander? Is that where he sat there before?
No, I don't know.
Yeah, I'm pretty sure Xander sits there. I don't think so. Yeah, I think it's just Okay, here we go. Pull your note back in, everybody, and let's finish up our last topics. Okay, so today, this unit is it's really big, as you are well aware, and it's somewhat well connected, and this last topic is connected, but it also feels a little not connected. What we're getting into today is we're talking about spectroscopy. Now, we've actually already learned about one type of spectroscopy. In Unit 1, we learned about photoelectron spectroscopy. And we learned how to interpret the graphs. They were the ones that looked something like this and under these things. You remember what these peaks told us? Yeah, it was 1s2, 2 peaks, 2s2, so on and so forth, right? Draw the scale at all. But today we're going to discuss 4 different other types of spectroscopy. Now, interpreting their graphs, we need to know how to do those ones from Unit 1. The other ones we'll learn, one of the types we'll learn later on. The other 2 we won't ever learn in this class, how to interpret their graphs. But you do just need to understand what they do and what information they give us. So why would I perform this particular test? Oh, because it tells me this information about my unknown. Okay? Now, in order to understand spectroscopy, we do need to make sure we first understand light, because all spectroscopies use a form of light. Now, we're familiar when we think of light as the light we see, but there's a huge range of what light is. But still think of them all as a flashlight. Okay? It's a flashlight. We just may not be able to see what it's shining with our eyes, but it still behaves like the light we know. Okay? Now, a more scientific word for light is radiation. Often radiation has a very negative connotation, right? On shows and things, radiation, we gotta get out of here, right? Which it can be, but radiation scientifically is just a form of energy that has wave-like characteristics and travels at the speed of light. So any type of light is a type of radiation. Now, there are harmful radiations, but there's also a lot of radiation that does nothing to us. And we'll look at the whole spectrum here in a second. All radiation travels at the speed of light, which is, put this up there, the speed of light is 3.0 times 10 to the 8 meters per second. So that's how fast light travels.
That's the two-way speed though? Because we can't measure the one-way speed of light, right? Is it possible to measure the one-way speed of light or only the two-way speed of light?
I don't know, Tyler. I'm not sure. Are you saying two-way speed because of how we analyze it because of bouncing back?
Yeah, because that's the only way we've ever measured the speed of light, right? Because you can't just anyway, it's hard to explain, but
I will go converse with our physics teacher down the hall after this and ask her thoughts. I don't know. That's a great question. Now, a few vocabulary as we talk about light we need to kind of be familiar with is first off wavelength. Wavelength defines itself, it's the length of the wave. So as the light travels, it travels like a wave. Wavelength is measured from crest to crest or from trough to trough because it's proportionate. But that's what wavelength measures. The other big measurement we talk about is frequency. Okay, frequency is cycles per second. Cycle meaning up down is a cycle. So how many up-downs does it go through in a second? Now, you've got to be cautious that frequency is not speed. Because what speed does all light travel at? The speed of light. So they all travel at the same speed, but they don't all have the same frequency. Nate?
Like gamma radiation, since that has mass, then it couldn't travel at the speed of light.
Say that one more time.
Gamma radiation has mass, so it couldn't travel at the speed of light.
So gamma radiation is still just pure energy as well. It comes out of things that have mass, like if you're thinking like a nuclear atom, but the gamma that comes out actually is just straight up energy. So it does still travel the same. The way you can kind of separate speed from frequency that helps is if you imagine a really, really tall person. So last period, Brian Felt was in my class, if you know him. So we used him as the example, because he's like, I don't know, 6'4", something like that. Okay, and then imagine a really, really small person. Okay, so Ryan said Sam Brand, if you know him. So imagine really tall, really short. Okay, they're walking through the hallway at the same speed. What's happening with their legs, though, if they're walking at the same speed? What's the tall person doing? Right, they probably take longer strides because they're tall, and the shorter person, right? But can they be moving at the same speed? Yeah, so that's the same thing with frequency, in that something can have a high frequency and something have a low frequency, but they get to the same point at the same time. Now, frequency and wavelength are inversely proportionate. It's impossible to have a long wavelength and a high frequency, right? As the wave gets longer, the frequency must get lower and vice versa. Okay? The other factor we'll get to in a second and then is how these relate to their energies. Okay? So this right here is the electromagnetic spectrum. It shows you all the different types of radiation, I guess, that we have named so far. Who knows? One day we may have more. So it starts with radio waves, microwaves, infrared, visible light, ultraviolet, X-ray, and gamma rays. Once again, these are all just types of light. But due to their frequency and wavelength and energy, what they do changes a lot. Now, our eyes can only see, once again, these ranges of light, right? Outside of that, though, there are tons, like around us right now, if we could see how much radiation there is, it probably would be like sensory overload, because like so many things put out some type of radiation.
Is it physically possible for like an organism to maybe see like infrared waves or microwaves?
So some, yes. So actually some animals can see outside of visible light spectrum. So snakes can see into infrared, so that's like heat vision, right? So snakes can see their prey through like the heat that it puts off. And then like bees, I know, can see into the ultraviolet region. So if you ever look up like an image of a flower to a bee, it looks really cool because it looks quite different to them. And I'm sure there's probably more animals, those are the only ones wild crats has taught me. I don't know outside of that, but I do know like others can see. Bigger range than that, I don't think, not that I know of, Tyler, like I don't think we know of any creature that can like have X-ray vision.
I'm just thinking like how crazy would it be to see radio waves like.
Oh yeah, radio waves would be insane, like in the world we live in today, right? Because every device we have.
But it works like with light, right? Is that why when you go into like the mountains, everything's kind of shut off because there's no way?
Exactly, yeah, because it's the same concept, and depending on how strong of a wave it is, determines how well it can pass through things, right? So literally, like when you think of an X-ray, so imagine I'm getting an X-ray of my arm, okay? It's just shining an X-ray flashlight at my arm. The difference is X-rays can pass through skin and tissue and muscle, but they can't pass through bone. So an X-ray is literally a shadow from the flashlight. It shines through what it can, but gets stopped by what it can't, and that's the picture that you get. Just like a regular flashlight shows you the shadow of my whole arm because visible light can't pass through any of it. Seth and Jake.
How come like it can pass through skin? Does it have to do with like density or like just?
Yeah, so it's a combination of the energy of the wave itself. So X-rays are a lot higher in energy, and so that higher energy allows them to penetrate, and that shorter wavelength too, allows them to penetrate deeper than like visible light does. But then bones are too dense for them to pass through. Yep.
So like, if a snake can see infrared, does that mean like it has a bigger range of like the light it can see, or just a different? Because like,
That's a good
if it can see
question.
infrared, does that mean it can see what we see too?
I'm not sure.
But
Yeah, I'm not sure if it's like, if it's bigger or if it's just shifted. I know with bees it's just shifted, like they don't like, because it just looks that way to
would
them.
there be a way like if you could see infrared, like you can't just switch
Yeah, that'd be cool. You'd be like, infrared mode.
Yeah. So like,
Yeah, I would guess, I don't know, I'd have to research. I would guess most animals who can see different, that's like, they can only see that range. They don't get to see the others. But yeah, that's a great question. I don't know. Nate?
Could you reflect it with like a mirror then?
No, depending on what it is. But like certain samples would stop it from penetrating through and would reflect it, right? So like when you get an x-ray, if you've had an x-ray done, what do they put on your body that's not being x-rayed? Lead. They put a really heavy like blanket thing, which is lead, because lead is so dense it can't pass through it, because they don't want to send x-rays like through all of your body, right? And so I guess in a sense the lead is kind of acting like a mirror and reflecting it, right? It's just different in that because we can't see it bouncing off. That's why like when the person who's giving you the x-ray, they like set you all up, but then they leave the room, right? Because even though the x-rays are being shown here, some of them could get deflected, right? So yeah, great question or connection to that. Bryn?
So when people like get radiation, is it just like shooting a flash?
Kind of, in a sense, yes. Or something is emitting that light that is then causing problems, right? So as we get down, so once again, so this is radio waves are the lowest in energy, longest in wavelength. Then as we travel this way, they get smaller in wavelength, higher energy, and this kind of shows you like their ability to penetrate. So this is why these ones are more dangerous to us, is because of their ability to penetrate at a much smaller level. So the idea of the Hulk, how is the Hulk created? Through gamma radiation. The scientific part of it is the fact that gamma radiation can penetrate your cells and mutate them. Now, that doesn't mean you turn into the Hulk, it just means you get cancer, because that's what it is, mutated cells, but the idea of it is, there's the science behind the Hulk, right? Another cool connection is we think about like a microwave, right? So a cool experiment you can do is if you get your microwave and you get like a king-size chocolate bar, you put it in your, well, you take out the spin plate and you put the chocolate bar in the microwave, okay? You cook it, not so much that it like melts completely, but just starts. And what happens is the chocolate bar will have actually two separate melted pools, which is literally showing you the length of your wave passing through it. That's why like often with a microwave, like you take a bite and one part is like frozen, but the other part's like lava, right? It's because it's a wave and it misses things as it's heating your food, right?
So is radio and like gamma rays like the limit of like how the wavelengths can get, or is there
Like big and small?
Yeah.
As far as we know, but in chemistry I never say never, because 5 years down the road maybe they'll discover something more, right? But yeah, as of right now, that's kind of where they've classified all the waves of it so far. Yeah.
How come microwaves like make metal freak out? Is it because it creates like, it moves the molecules so much that the electrons can travel kind of through?
Yeah, so we'll talk when we get to the microwave. So the way it heats your food is microwaves have enough energy to cause the water molecules in your food to spin, and they rotate. And then that rotation of the water heats it up. But if you put something in the microwave that doesn't have water, and based on how metals are with their electron C, as it hits those, then it just causes the electrons to start to jump. Because a spark is literally a jumping electron. Like when you see a spark, it's electrons, right? Electricity. So that's what it's causing, is it's just causing the electron C to like freak out. So yeah, that's why you don't put metal in your microwave.
What would happen if you like got rid of all the water molecules in food and then like put it in the microwave?
What do you think?
Just
The same thing?
Just sit there.
Yeah, so then it most likely will light on fire, because instead of having something to like just spin, right, then the energy just, so don't do that either.
Food in toaster in your microwave.
Oh, really?
You didn't remember that that was in the microwave. So then I like turned around and see the microwave.
Is it going crazy?
Is it
Okay.
Okay. All right, let's talk about the different types of spectroscopies. So once again, the biggest thing you need to know is connect the type of spectroscopy to what information it gives us. Like, why would I perform this test? Okay, this is the one we've already covered, so here's our PES spectrum. This is the highest in energy in terms of test we use. Obviously, gamma is higher, but in terms of a chemistry test, we don't really have a spectroscopy where we use gamma. So X-ray spectroscopy is literally shining an X-ray at an atom. So here's our atom. Okay, here's an electron. I shine the X-ray at the atom. The X-ray has so much energy that when the electron takes it in, pew, it comes flying off. Right? So the electrons get ejected from the atom. Which is then how we get these graphs. Because as they get ejected, it detects how many electrons were ejected at that particular energy, and then that's how we then could identify an unknown element. Alright, so this is a great tool to use if you have a sample of an element and you have no idea what it is. A PES spectrum can help you determine that. Michael?
So if you get X-rays, do electrons just fly off your hands?
Great question. No. So keep in mind with the electromagnetic spectrum, X-ray is a category for a large grouping of it. And then there's also, we won't deal with it a ton, but you can also control the intensity of it. And so that's what's happening here. Obviously though, if it was like a high-powered X-ray, yeah, it would not, your body would fall apart. So, not good. Okay, PES spectrums. Next one is ultraviolet UV visible light spectrums. They're two types of light, but we classify it into one category of how we use it. So these ones are our medium strength of energy. And for this one, we will do a lab on one of these, but we're gonna do it we do a few labs during our review month right before the test. And this is one of those labs we do right before it. So we'll kind of learn more about these graphs later. For now, just right now, so the same thing is happening. I should get my picture here. Right, so we're shining our light. Okay, but now it's not as strong as X-rays. So instead of getting ejected from the atom, this time the electron just jumps up to a higher energy level. And in that process, we're able to identify things about the element. So this one is a transition of the electrons. So the first one was ejecting the electrons. This one is, they're just transitioning to a higher level.
What's the relative energy?
Medium. So those are medium strength. And I should have just made these both one box because it's the same movie. So it's the same for both. So just write it in one, draw an arrow together. Alright, so X-ray, UV visible light. Lower in energy is we have, I went the wrong way, is the infrared test, so IR. This one creates really fun looking graphs. They look something like this. Okay, I always forget the word. What are they called in caves? There you go. That's what these always look like to me. You won't need to know how to interpret these. If you go on to take organic chemistry later, you'll learn how to, which is really fun. The basic idea here is, so it's lower in energy, right? So this is pretty low energy. So keep in mind, the lower the energy, the less of a change. So X-rays ejected electrons, UV transitioned electrons. Now it's getting to the point where it's too big to change the electrons, like those are so small now in comparison, but it can change what we call the vibrational levels of the molecule. Now, the word vibrational, when we use it in chemistry, maybe has a different visual than what you think. Like when you think vibrate, I'm guessing most people think of like your phone and like this, right? When we're talking about vibration of a molecule, we're actually talking about within the bonds themselves. So when you have a molecule like water, right, so water is bonded like this, okay, even though it is in a bent shape, the bonds aren't as stagnant as we often make them, and they vibrate. The way they vibrate are in a variety of ways, and we'll see this in a later unit. But so for example, like if my head is oxygen and my arms are hydrogen, so see like my bent shape, right? So when we talk about vibration, it's like the bonds going like this, or like this, or like this, right? So that's what we mean by the vibration of it, is the bonds actually can change how they're moving. And what scientists have found is that certain bonds always vibrate and send the same signal every time. So how you interpret these cool graphs is that a certain section will always look the same for a certain type of bond. So for example, just to give you a sneak peek of what it looks like, this little section right here, at this wavelength, always corresponds to a C-double-O bond. So what's really cool is using this, it actually breaks down the entire structure. So you can piece a structure back together by decoding one of these things. Once again, you won't have to do that in this class, but it's kind of cool. That's how it's really helpful, is it can help you identify how things are bonded, which in organic chemistry is really helpful because the molecules are so big, right? It's not like simple Lewis structures. They're all like this type of thing or bigger, but you could identify like, oh, hey, this structure has one of those hexane circles. Oh, and it also has an N to O bond, and like so on and so forth. Kind of.
How do infrared cameras work?
Let me ponder how I can explain that. Besides, they work through IR. But I don't know, in terms of like how our eyes, yeah, I'll think about how I can explain that and get back to you with an answer. So, good question though.
Yeah.
All right, last one is our lowest. Once again, now we're down to just shining microwaves at an atom. So we had ejection of electrons, transition of electrons, vibrational levels, and now what did we say the water does in a microwave? Yeah, so rotational levels. And then through this rotational one, it's actually a way where you can identify hydrogens connected to a substance. So that's kind of where scientists might use this test, is to help them identify that. So, okay, questions on our 4 different types of spectroscopies.
Does radio spectroscopy exist?
Not that I know of. It's too big to influence atoms. Yeah, I guess even a high intensity radio wave doesn't do anything. That's my guess at least. So, okay, now let's talk about the calculation side of frequency, wavelength, and energy. Okay? So our equation for energy that connects to frequency and wavelength. So let's write, there are meant to be 2 boxes, but one of them kind of disappeared. So just in this space next to that box, write another equation. So our first equation, okay, so we have C is speed of light, that's the symbol for wavelength, and then wavelength times frequency, which frequency is also a Greek symbol, it's not the letter V. It pretty much looks like a letter V, but that's why it's kind of a straight line than a curved line. Its name is nu, so this is the symbol for frequency. So wavelength times frequency equals the speed of light every single second. Okay? This is on your formula sheet, by the way. The variables are defined on your formula sheet, so you don't have to memorize it, just need to use it. Okay? The second equation we have is energy is equal to H times frequency. So energy is E. This is once again frequency, same variable. H is Planck's constant. joules per second. Once again, it's on your formula sheet. It's a constant, never changes.
What's J over S? What does that stand for?
Joules, which is a measurement of energy. So how much energy per second? So the idea here is and Einstein's actually one who is credited with this discovery. This actually later links to like E equal mc squared. We won't cover in this class, but if you ever wondered why, like where that comes from. But this idea of energy is interesting. Energy and light has this weird relationship where to us, it behaves continuously like a wave. But if you actually get down to the molecular level, energy behaves as what we call a photon, which is a particle of light. So energy has this like wave-particle duality, where to us it looks like a wave, but in actuality it's actually a photon due to the fact that we are so far zoomed out of what it is. So kind of an analogy to think of is that if I had a staircase, okay, but the steps were teeny, tiny, if you're far away, what would the staircase look like? A ramp. It wouldn't actually look like stairs, right? And that's how energy is to us. To us, energy appears continuous. When I look at these lights, there doesn't seem to be any breaks in between. It seems like it's continuously coming out. But actually at the molecular level, it's actually like tiny little balls of, that's what a photon is a ball of light coming out. But to us, it feels continuous. Planck's constant is the size of the staircase steps. So this is how small of a difference there is between energy levels, which to us is too small to register. Seth?
So is that like why like when you like record something in slow-mo, like the lights flicker?
Yes, you can kind of start seeing it somewhat, especially nowadays with how slow-mo can get, right? Is exactly right. Yep. Okay. Let's try, any other questions for now before we try a problem? Okay, let's try this problem together. All right, so we have this diagram here. Okay, those are our lights. We're shining the light on. It says, that diagram represents the photoelectric effect for a metal. When the metal surface is exposed to light with increasing frequency and energy of photons, electrons first begin to be ejected from the metal when the energy of the photon is 3.3 times 10 to the negative 19 joules. Question A says, what is the frequency of light? The light. That's weird. I don't know why. Of the light. What I should have said. Okay, so we have two equations. Let me move them over here. So we have this equation, and we have this equation. Once again, they're both on your formula sheet. The catch is just knowing when and which one to use. So what am I trying to find on part 8? Perfect. So circle that word frequency. Then I go to my equation. So this is how, like, when you're using your formula sheet and you're like not sure what to use, this is how I start. I say, okay, well, what variable am I trying to find? Frequency. What's the symbol for frequency? The V guy, right? So either of these equations find frequency. So then the next thing we look at is what info did the problem give us? So up above, what information do I have? I have energy. So this is the equation I want to use because I have E and I want this. So I'm going to take this equation, I'm going to rearrange it so frequency is on its own. So I'm going to divide H. So E over H equals frequency. Good as E. Okay. All right, what was the energy? 3.3 times 10 to the negative 19 joules. I'm going to draw an arrow to show you just got that from the problem. Then H is, good, Austin, just that constant, right? 6.626 times 10 to the negative 34 joule per second. Once again, it's on your formula sheet, so you don't have to memorize it, but it's there for you. And And then at this point, your calculator does the heavy lifting. Just plug it in. You do have to be cautious with times 10 things when you're typing them in your calculator. You've got to make sure this stays as a group when you divide it, right? Otherwise, order of operations gets messed up. So I got 4.98 when I typed it in, times 10 to the 14th. That's what my calculator gave me. Questions on the setup for that problem? Any thoughts on my final unit? Close. So the joules go away, so seconds is the only thing left, but it's still on the bottom of the fraction. Because what is this measuring? Frequency, which is cycles per second. So it's a weird unit because it's per something, but there's no unit on the top. In a sense, I guess the word cycles is on the top, but you don't typically write it. You also can, just so you know, if you see it, or if you want to write it, you can also write it as 4.98 times 10 to the 14 s minus 1. Because a negative 1 exponent means it's on the bottom of a fraction. So this is the same thing as this, which is also the same thing as a hertz. So if you've ever heard the measurement of a hertz before, that's what a hertz is per second. Cycles per second. So just know all those units mean the same thing. So
Are the equation?
I don't know.
I'm so confused.
It's Friday. Hertz, there you go. 8.
Hey.
Harsh.
Wait, so wait.
Let's see what it says.
Okay, figure it out. Many.
So is the number 6.626 or 6.262?
626.
I think it's 626. Did I do it wrong? Is it on formula sheet
You
handy?
just did like
Mine's-
when you were. When we
Did I do it one way that time and then one way this
Yeah.
time? Oh, my brain, I don't know. Where's the formula sheet?
It's 6 to 6.
6, this is the right one? Okay.
I got the
This,
same
did I write 2, 6,
2.
2?
Yeah.
I did before? My apologies. 6, 2, 6.
answer.
Okay, any other questions or clarifying on part A? Okay, part B says, based on the data table, what would be the color of the light? Now, if I come here, we have colors. What are they measured by though? Wavelength. What do I have right now? Frequency. So we have to convert and get to wavelengths. So this is the symbol for wavelength. So that's the equation I'm going to want. So I'm going to rearrange it. So wavelength equals C over frequency. All right, C is the speed of light. 3.0 times 10 to the 8. Is that how it is on your formula sheet, or did they give you more decimals? Did they do the 2.99?
I do 2.998.
Oh, okay, so technically on your formula sheet, I guess it's 2.998. That's the one I have memorized. Is pretty much 3.0 for that. All right, and then the frequency is what we found in the problem before. So 4.98 times 10 to the 14. Plug it in. So on this one, I got 6.02 times 10 to the negative 7. Questions on the math side of that? Good, Robbie. Yep, so the unit of this would be a meter, which is slightly problematic to getting to our final answer, because our table is not measured in meters, it's measured in a nanometer, which is nm. So we need to convert meters into nanometers. So about nanometers very much, so, but anyone know how the difference? So there's 10 to the 9 nanometers in 1 meter. So what is that, 9, is that a billion or a million?
Thought it
So 10 to the 9 zeros,
was,
Yeah, it's a billion.
that'd be billion, right? So it ends up being 602 nanometers.
the color of light is in nanometers?
Yes. So then,
Oh, yeah.
what color is my light? Questions on using these two equations. Once again, they're not too, they're pretty simple, but you gotta be careful with units. And then just the setup of where you put stuff. Okay, so we're stopping there. 3.13, Beer-Lambert's law, is the last thing, but we're gonna wait because that goes with that lab we're gonna do. So we're just gonna learn it all then. So it won't be on the test. You don't need to know how to do it. We'll cover it later. So miracles do happen where we're done and there's still time left in class. So you have plenty of things on your to-do list. So the newest homework assignments are 2 AP classroom quizzes about what we learned today. Just 4 pages of reading. And then that's it. So you are welcome to work on AP classroom quizzes. You're welcome to work on any homework assignments. But if you are on your phone or not doing chemistry, then I'm going to give you the test today. That tells me you're ready if you're not working on things, right? And it's ready for you. So if you want to take it today, you could. Otherwise, use this time, come ask me questions, work with each other to get stuff done, okay?